Welcome. We are working our way through Chapter 9 on division, and today we look at division properties and algorithms, with really a focus on the algorithms part. We'll see two algorithms, the standard algorithm and the partial quotients algorithm. Now, remember, in our models section, we had two models, the how many in each group model and the how many groups. So those two models, we will see them reflected in our two algorithms. All right, let's take a look. The first is the standard algorithm, or long division. So let's say I want to figure out 852 divided by 3. We write 3 into 852. And now we proceed. We think digit by digit. 3 into 8. How many times does 3 go into 8? Well, it goes in 2 times, and 3 times 2 is 6. So I subtract. 8 minus 6 is 2. Bring down the 5. New problem. 3 into 25. How many times does 3 go into 25? Let's see, 8 times. 8 times 3 is 24. Subtract, bring down the 2. 3 into 12. How many times does 3 go into 12? 4 times. 3 times 4 is 12. I subtract, I get 0, and that's the end of the problem. So 852 divided by 3 is 284. Now, there is another way that's actually not taught all that often, and that's short division. Now, it's basically the same procedure. I would write down 3 into 852. Oh, and by the way, this is the method that I was taught by my mother. I have a fond memory of sitting at the kitchen table with my mother, and she taught me how to do short division. And for me personally, I much prefer doing short division rather than long division. It does require a little bit of mental math, but not too much, and it saves you a lot of space. So here's how short division works. 3 into 8. 3 goes into 8 2 times. So 2 times. And I think to myself, 3 times 2 is 6. Oh, but 6 doesn't quite reach 8. I've got 2 left over. So I'm just going to write my 2 as a little subscript in front of the 5. And now I think 3 into 25. The 2 and the 5 make 25. 3 goes into 25 8 times. And so mentally I'm thinking 3 times 8 is 24. 24 falls short. I've got 1 left over. So I write the 1 for the remainder, 1 left over, as my subscript, and now I have 12. 3 into 12 goes 4 times. And that's it. So I've solved the whole problem with a lot less work being shown. Now this is great if you have a problem like 5 into, I'll just make something up, 9, 4, 3, 1, 6. You can tell this would require a lot of work down below if I was using long division. But with short division, we think, well, 5 goes into 9 1 time with 4 left over. 5 into 44 looks like maybe 8 times. 5 times 8 is 40, so that leaves 4. 43, so 5 into 43 goes 8 times. That's 40 with 3 left over. 5 into 31, so 5 goes into 30 6 times. 5 times 6 is 30. I have 1 left over. 5 into 16, that goes 3 times with 1 left over. Oh, and what do? Maybe at this point I can write 0.0, so the 1 that was left over comes in front of the 0. 5 into 10 is 2 times, and there's the solution. So I do have to do a little bit more mental math, but I save myself all that work down below. So why does this standard algorithm work? Oh, and by the way, I should mention, these two methods really are essentially the same thing. It's the same process. Both of these things could be considered the standard algorithm. For long division, I'm just showing a lot more of my work. So why does this standard algorithm work? And that's an important question, because you probably know the process, but why is that the correct process to use when dividing? And so here's a little demonstration coming up next. I really like this demonstration. Suppose 3 friends need to split $852. That was the problem we just had. 852 divided by 3. So I start off with 8 hundreds. Oh, check. They really have $852 to split. So the 8 hundreds, I split those as evenly as I can. So each person gets 2 of those 100s, but we have a couple 100s left over. So I can't split those evenly. What'll I do? Let's convert those hundreds into tens. Now I have a whole bunch of tens. In fact, I have 25 tens. So now let's try our best to split those 25 tens evenly. Each person will get 8 tens, but then I have a single 10 left over. I can't split the 10 among 3 people. Oh, but here's what I can do. I can take that 10 and convert it into a bunch of ones. Now I have 12 ones, and let's split those 12 ones. And there it is. Oh, and now they're happy. So going down from hundreds to tens to ones, I split at each time as best as I can with some remainder, and then whatever is my remainder, that gets converted into the next level down. So that's why the process works. Which model does the standard algorithm follow? Do you think this reflects more of the how many in each group, or do you think this looks more like how many groups? And it really is the how many in each group. So when we see the picture down below, and just to look at the algorithm again, so 852 divided by 3, I have my 8 hundreds, and each person gets 2, the best I can, and then I have 2 hundreds left over. I convert the 2 hundreds into tens. Now I have 25 tens. 3 into 25, how does 25 get split up? Well, 8 tens, but then I have a single 10 left over, and that makes a bunch of ones, 12 ones, and then 12 ones divided by 3 is my 4. All right, let's take a look at our second algorithm. This second algorithm is called partial quotients, and it reflects the other model. It reflects the how many groups model. So when I see 962 divided by 6, I really want to think of it as 6 into 962. How many sixes are in that number? And we might start off by making an estimate. That's what's actually kind of cool about this idea is we're making approximations and estimates. And maybe 100, you say 6 goes into 962 at least 100 times, probably more. But if I think 100 sixes, so I put the 100 on the right, that'll account for 600, and then I do a subtraction. 962 minus 600 is 362. So now, here's my new problem, 6 into 362. How many times does 6 go into 362? And maybe we'll make an estimate, say, well, 20 times, probably goes in at least 20 times. So I do 20 times 6, and I get 120, and then subtract. 362 minus 120 is 242. And so, well, let's see. When I put in 20, I got 120. So if I put in 40, I get 240. Do a subtraction. So now finally, I add up all these numbers on the right. 100 plus 20 plus 40. And these were all the groups of 6 that I accounted for. So altogether, I had 160 groups of 6 with 2 left over. And that is, in a nutshell, that is our partial quotients algorithm. Here's another example with exactly the same division problem, but you can see you can take a different route to get to your solution. You start off with 100, but maybe the next time you try 30. 6 times 30 is 180. You subtract that off. 182. Try 30 again. 180. And so there are different ways that you can get to the same solution. And like I mentioned, this algorithm reflects the how many groups model. These are the two models. Give them both a try in the worksheets. One thing that's kind of cool about partial quotients is that there's no one way to get to the right answer. But on the other hand, the bad point is that it requires just a little bit of insight, but some experimentation, and that's a good thing too. Give these things a try. Go through the worksheet, check your answers on the worksheet, and of course, let me know if you have questions.